Remember that you have learned what chiral means. That means handed, and that a tetrahedral atom with 4 different groups is chiral. I'm going to show you why this makes 2 different non-superimposable mirror images. Here you see the carbon and a carbon. On that carbon you have 1, 2, 3, 4 different groups. You see they're different colors, so they're different. This is a mirror image. Now what I'm going to do is I'm going to take these 2 and I'm going to turn this around in space and try to superimpose them. So I'm going to turn it and move it over, and you can see that the yellow and the pink line up, but the red and the blue have switched place. And this the colors are wrong here. It should be the PowerPoint changed the colors on me. But you can see the whole idea. 2 colors are the same, 2 colors are different. You can't superimpose these. Now, if I look at this, we call them enantiomers because they are chiral carbons and the mirror images are non-superimposable. So what you do is you look for 4 different groups attached to an atom, and then we will know that it is chiral, and it makes 2 non-superimposable structures. A lack of symmetry is what causes the chirality. So if visually you can see a plane of symmetry or a center of symmetry, we have an achiral molecule. If you don't see a plane of symmetry, still you need to not say it's achiral unless you check every atom to make sure that each atom is achiral. So what do you need to know for an exam? Be able to find a chiral carbon by looking for 4 different groups, and then be able to identify enantiomers. Enantiomers have to have a chiral carbon and be mirror images of each other. Be sure to notice, because a double bond has only 3 different groups on it, you can't have a chiral carbon there. It has to have 4 groups. No atom in a double bond can be chiral. Also, if any 2 groups are the same, and this means not just the first atoms, but the atoms after that in the group, if any 2 groups are the same, the atom's achiral. So now what do is we'll look at an example here. First of all, do you all see the plane of symmetry here? Some of you may not. But if I cut this molecule in half, it would have half a carbon atom, half an oxygen, and half a hydrogen, and then this part would look exactly the same. I can tell by looking at the individual groups. This has 3 hydrogens, this has 2 hydrogens, and this has 2 groups that are the same, an ethyl and an ethyl. So that cannot be chiral. This is the same as that. This is the same as that. So there are no chiral carbons, so the molecule has to be achiral. If I look at this one, I can see 3 hydrogens here, 2 hydrogens, 2 hydrogens here. Those have 2 groups the same. But if I look at this carbon, I will see that this carbon has a methyl, then a 3-carbon chain, a propyl, a hydrogen, and a hydroxyl. 1, 2, 3, 4 different groups. So it has a chiral carbon, and because of that, it's a chiral molecule. So now what I want you to do is determine which ones of these are chiral carbons, which are molecules that are chiral. Well, if I look at this first molecule, you can see these carbons cannot be chiral, but this one has 4 different groups. What are the 4 different groups? A hydrogen, a bromine, a methyl, and an ethyl. If I look at this compound, I know these 2 carbons cannot be chiral because they have a double bond. And these cannot be chiral because they have more than 1 hydrogen on each of those atoms. Can this be chiral? A lot of you would say yes, because you think you see 2 different groups. But look, this is one group, This is another group. Then we have an ethyl here. And what's this? An ethyl. Well, you have two groups that are the same, so it is achiral. Okay, let's look up here. If I look up here, I can see there is a double bond here, so neither of these carbons can be chiral. This has two hydrogens and this has two hydrogens, so they cannot be chiral. What about this? Well, this side is different from this side, so that's two groups. Then there's a chlorine, three groups, and a hydrogen on here. So this carbon is chiral. If I look at this molecule, I would say, yes, we have a chiral carbon here, no chirality here, and then a chiral carbon here. Why? This group has a methyl and a hydrogen, and the side of a ring that looks like that. Okay? This has a methyl and a hydrogen, and then a side of the ring that looks like this. But this side of the ring on this carbon is different from this side of the ring. And this side of the ring is different from this side of the ring. So you have to, on the rings, you have to kind of look around the chain to see if it is the same, a mirror image. So that's not chiral, but these two are. Why is this important? Well, biological molecules like enzymes, sugars, they're all chiral. Your body's chiral. If you were to look at the mirror image of yourself, you would see that in a mirror image, your heart would be on the right side rather than the left. And this chirality extends all the way down to the teeniest, tiniest little molecules in there. You have so many chiral molecules that the chirality of those biological molecules makes them very specific in the way that they work. So you can look at the active site on an enzyme in your body as being like a glove that will only allow a right hand in, not a foot, and not the left hand. And so they're really specific in the way they act, which makes you allows you to have very complex biology. So the reason this is important is because it reduces the selectivity of, or enhances the selectivity of biological molecules. Most drugs are chiral. When you look at chiral drugs, they're usually sold as a mixture of enantiomers because the chemical processes that we have to make chiral compounds are very limited, and what we end up making is a big mixture of both enantiomers, and we call that a racemate or a racemic mixture. Usually in those drugs, only one enantiomer is the active compound, and the other enantiomer causes side effects. And that's a problem. For example, Xopenex is one enantiomer of albuterol. And if you use Xopenex as a bronchial tube relaxer, then what happens is all it does is relax your bronchial tube. But if you're using albuterol, it has both enantiomers, and one of them relaxes your bronchial tube, but the other one causes your heart rate to speed up, which can be dangerous in some people. Thalidomide has one enantiomer that just reduces morning sickness. The other enantiomer causes birth defects. There's a real sharp example of a problem with the enantiomer. Usually the enantiomers are competitive inhibitors, or they may not be active at all. But with some compounds, the enantiomer characteristic is a problem. So how do you identify enantiomers? What you first do is you identify a chiral carbon, like we've already gone through. Then you can take another compound and bring it up to see if it is a mirror image. If it is a mirror image, well, then you have enantiomers. So look at these compounds and you'll find a pair of enantiomers in there. Find them. Well, if I look at these compounds, I will see that this and this are mirror images. This is totally unrelated, and this is very similar, but it's still not the same. So these two are mirror images, which I'm showing you with the dotted lines. Are these enantiomers? No, there's no chiral carbon. If you look right here, you can see there are not 4 different groups. There's only 3 different groups. And even though this is a mirror image, it's not an enantiomer because this is the same as this. And if I flip this around this way, you would find you can fit them inside each other. So they're superimposable and not chiral.